We often hear expressions like, it's all relative, or everything is relative in our everyday activities. In fact, it's all relative when we say one man's trash is another man's treasure. Well, today we are going to talk about relative motion. Relative motion is a very important concept with serious application in our everyday life. The objective of this short presentation is to help you develop an understanding of relative motion and introduce you to the engineering notation that goes with that. Do you know relative motion is the reason why some people get car sickness, seasickness, or air sickness are all forms of motion sicknesses. We get car sick because our brain is receiving conflicting information from two sources, our eyes and ears. When we are in a moving car, our eyes can look at the floor or look at the driver right next to us inside the car and make us feel that we are not moving. On the other hand, our inner ear, which can detect motion and stability, sends an information to the brain that we are moving indeed. So our eyes are saying we are not moving, our ears are saying we are moving. This conflicting information causes the brain to confuse, and that's how we get car sick. Some people believe that brain is duped into thinking that we are poisoned, so it reacts. That's why you throw up. Of course, there is more to relative motion than explaining the reason for getting car sick. Let's talk about mid-air refueling. Planes flying at 300 miles an hour at probably 30,000 feet. And when they refuel, every operation should be precise. It's a difficult operation, and if there is any relative motion between the planes during this operation, that would be a serious disaster. Or think about a more mundane everyday activity such as driving. Right? Driving, changing the lanes, passing a slower vehicle. All these activities are examples of relative motion. So relative motion is a critical issue in many applications that we deal with every day. Let's start with an example. Imagine yourself sitting at a coffee shop and looking through the window. Let's say you see a train pass by at, say, 50 miles an hour. Let's call this train A. As far as you are concerned, you are sitting, meaning you are stationary. Or we would like to say you are at rest. In this case, you see the train moving from left to right. From your perspective, or I would use the term your frame of reference, the train A is moving at 50 miles an hour. This is an easy to understand scenario. However, for a person sitting in the train, with respect to his reference frame, it is going to be a different story. He is going to see you as moving 50 miles an hour in the opposite direction. Well, who is right? As you can imagine, both cases are true, and both are using different frames of references. All right? Now let's take a closer look at this scenario. Let's draw a line showing my position at the coffee shop, and this is my reference line or frame of reference. And I denote this line with a coordinate system, and my absolute, the center of the coordinate system is 0, 0. Now, as the train moves, the position of the train with respect to me, that's my reference frame, is shown using a position vector r sub a 0. This is the change of position of train with respect to our fixed frame of reference. Now, let's assume there's another train B traveling in the same direction, and its position is shown further down and denoted as r sub b naught. So, from your basic vector algebra, you can write a simple position equation as shown here. R sub b naught is equal to r sub a naught plus r sub ba. Now, this is basically what this means is position of B, train B is equal to position of train A plus position of train B with respect to A. Now, I want to make a little simplification here. When we talk about position or velocity or acceleration with respect to a fixed frame, non-moving frame, we normally use the word absolute. In such cases, we do not use a second subscript, in this case 0 or not, in our notation. So we are going to drop this subscript and denote our equation in a slightly different way. As you can see, now the new equation is r sub b is equal to r sub a plus r sub b with respect to a. Notice there is no 0 in this. R sub b means its absolute position of train B with respect to a fixed frame. All right. I also want to draw your attention to the second term, r sub ba, and I want to make sure you can read this correctly. We read this as position of B with respect to A, or you can also read this as position of B relative to A. It's important for you to understand this terminology and use it properly. Also notice from vector algebra, you know r sub ba is not the same as r sub ab. So please be careful and do not interchange those subscripts incorrectly. So we have our first equation describing relative motion of two objects. And if you would like to read this expression one more time, it's going to be position of B is equal to position of A plus position of B with respect to A. Please practice and learn to read this correctly. We can also rearrange this equation in terms of the relative component. Now I would like to move on to talk about other quantities that you can derive from this equation. You have a vector equation involving position. Now, as you know, rate of change of position is velocity. So if we differentiate this equation, we are going to get a velocity equation which is going to read as velocity of B equal to velocity of A plus velocity of B with respect to A. Similarly, we can also write another generic equation for acceleration by differentiating the velocity equation, and that would be acceleration of B equal to acceleration of A plus acceleration of B with respect to A. With this basic introduction, we are now ready to deal with real problems. Let's take a look at an example for relative velocity.